All right, hello everyone. Today's lesson is on section 10.3, the last lesson in this chapter. This is another chi-square test. This is called the chi-square test for independence. Let's see here. So the chi-square test of independence is going to test independence in a better way than we tested it back in chapter 6, which was actually the first chapter for us. You may remember back in chapter 6, when we tested independence, we had to show that the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. It doesn't matter which one. We had to show both of them, actually. But I mentioned back in that chapter that this was kind of not the best way to check for independence because I don't know if you remember, but maybe you had an answer like 31.2% and the other one's 30%. They're not equal to, therefore you would have said not independent. However, they were so close, you said, well, you know what, for all intents and purposes, they probably are independent. So what do we do? Like, how far is that cutoff? So this test that we're going to do today, the chi-square test for independence, will take care of that for us by finding a test statistic, finding a p-value, doing all those same sort of things. So this is actually the same problem we did in chapter 6. I don't know if you remember or not. This is the data from the Titanic. Whether or not a person survived or not. Over here on the vertical column and the horizontal, we have the class of travel, first class, second class, and third class. So this is our actual data here in a matrix, just like it was for the chi-square test of homogeneity. The other ones are the totals. We don't really need them. So what you're going to see in this is that the test is going to look and feel exactly like the chi-square test of homogeneity. Basically, because it is. I'll just tell you the minor difference at the end here. But the idea is we're going to find the expected values. The expected values will be found the exact same way we found them before. So in other words, you would look at let's do this expected value. You look at so it's the same thing for the cells. Remember, it's row total times column total divided by the total. So this is kind of the quick way to do it. But also, you could just do like the overall survival rate. If you look at 499 out of 1360 survive, 499 divided by 1316 survive, so it's like 37.9%. And then you multiply that by, let's say, the first class, which is 325 times the 325 gives you, for the first class survival, 123.2. Okay, so we're going to do it's the exact same math as last section. The only difference is going to be in our null hypothesis and our alternate hypothesis, because in our null hypothesis before would have been the proportion of people that survived is the same for first class, second class, and third class, which in some ways is like independence for sure. There is a little minor difference, which we'll talk about here at the end of this lesson. But now my null hypothesis is just going to say travel of class and whether they survived are independent, or the alternate would be that they're not. Okay, so same conditions. I'm not even going to write them down. Sorry. Same conditions. So these are the expected cells, first of all. Sorry, there they all are. So we can find the test statistic here in just a second. The null hypothesis for this problem would be, class and survival are independent. That's my null hypothesis. My alternate hypothesis is not independent. We're going to find the test statistic the exact same way we found it before. So let me show you that. There's the test statistic. And the degrees of freedom, sorry about that here. Degrees of freedom is found the exact same way. So we did those rows -1 times columns -1. So this is a 2x3 matrix. So let's just go through the work. Whoops, let's not draw that normal because it's not really normal, right? It's skewed right. So it's kind of like this. We have a critical value, which we're going to find by using the chart. So the degrees of freedom it's a 2x3, so 1x2, 2 degrees of freedom. I'm going to go to my book right here, my book. go to the chi-squared chart. You can do this in your note sheet also. Remember, there is no inverse chi-squared button on the calculator. Otherwise, we could use that like we did inverse norm. So chi-squared critical values will go 5%. 2 degrees of freedom is 5.99. I happen to already do the math for this one. By now, I think I will have shown you how to do this on your calculator. It's the chi-square test. Hopefully I did that already. If not, you would just put the observed values in list 1, the expected values in list 2 for now, and then do a list 1 minus list 2 squared over list 2 to find that test statistic. I got a test statistic, which is chi-squared. Whoops, sorry about that. Chi-squared, which is about 133. It's gigantic, which you would expect. Look at how far apart those numbers are from where we expect them. P-value of basically 0, which means we're going to reject the null. And evidence that class and survival are not independent, which I think you would probably know just by looking at the chart from the beginning, right? If you were in that first class, you were a lot more likely to survive than if you were in the third class. So the test is going to look and feel exactly like the chi-squared test of homogeneity. The only difference is in your null and your alternate hypothesis. The conditions are the same. The expected values are found the same. The test statistics found the same. The p-values found the same. The critical values found the same. The only difference is in your hypotheses. So the weird thing about this is, how do you know? So if it's the same, how do you know? It sounded like homogeneity. By the way, if you go back to the original problem, I could have said something like, show that the percent of people who survived is the same for first class, second class, third class. I just worded that as a test of homogeneity. Okay, so the question becomes like, what's the difference, right? What's the difference between homogeneity and independence? Like, how do you know which one's which? So often you don't. If all I did was give you this chart and said, do a test, you would not know if it was independence or homogeneity because you could set it up either way. So, but there is a distinction between the two if you know how the problem's set up. So here's the distinction. The distinction is that the test for independence has one overriding population and 2 traits. Okay, so if we're looking at the Titanic, the population would be everyone on the boat. We'll just say everyone on boat. And then the traits would be, the 2 traits would be, one trait would be class, right? And one trait would be, did they survive or not? So that would be an independence test. A homogeneity test, multiple populations and 1 trait. So maybe some of you right now are saying, well, what's the difference? Couldn't I say class 1 is 1 population, class 2 is a second population, class 3 is a third population, and the trait is whether they survived or not? And the answer to the question is yes, you could. You would still not know which test. If all I did was give you that data in the chart, you would still not know which test because you don't know, well, which is it, an overriding population or is it these individual population? It's all on how you take the simple random sample. Now, this problem is not a simple random sample. So that's why I would have to ask you. I would just say, do a test for independence. So by the way, if they say do a test for independence, it is a test for independence, right? But if they just say perform the appropriate test, you need to figure out which test it is. So the way you know, because like, again, go back to this problem, you don't know overriding population with 2 traits, 1 population with 2 traits, or 3 populations with 1 trait. You don't know. So the way you figure it out is how the simple random sample was taken. So in other words, let's pretend this was a simple random sample. So let's say we didn't sample everyone. If I said, take a simple random sample of everyone, I have just made it 1 population. 1 population, therefore independence. But let's say I took a simple random sample of first class travelers, second class travelers, and third class travelers. So in other words, stratified, right? That's what we call the stratified sample back in chapter 1. If I did it this way, now it's 3 populations. So now it's homogeneity. So somewhere in the problem, they're going to have to tell you they're going to say, hey, we took a simple random sample. So let's talk about high school. Let's say I say high school and I say grade, and I don't know, we'll say walk to school or transportation to school. So, we did this little chart here. We got 9, 10, 11, and 12. And we got car or bike, let's just say. Okay. So again, the way it looks right now, it could be either test. So you have to read into the problem. If someone says, hey, we took a simple random sample of 200 students at Mountain View High School, and then we asked them, what's your grade? And do you ride to school or bike to school? Drive to school or bike to school? The way I set it up was I took a simple random sample of the whole entire class, so that would be independence. However, I could have done a stratified sample. I could have said this. Hey, I took a simple random sample of 50 ninth graders, 50 10th graders, 50 11th graders, and 50 12th graders, and then asked them, do you drive to school or bike to school? That would then be homogeneity because I set it up into different populations. Just depends on how the sample is taken. So either they're going to tell you how the sample was taken, or they're just going to tell you which test to do. So that's it for chapter 10. I'll see you in class.